Thank you. Thank you, Laure. Thank you very much for the invitation. As Laure said, I'm going to talk, well, you didn't say it actually, but I'm going to talk about crowd motions. I must warn you, you might imagine, since I'm going to talk about human beings, you might expect, perhaps hope, modeling a very sophisticated behavior, ability to develop strategies. Actually, that will not be the case. In some situation, we have actually to model that kind of thing, and I will be happy to answer questions about that. But since I wanted to show you some formalized things, I chose to focus on a very particular aspect on crowd motion modeling, which is not actually the human behavior, but more congestion. There's something that is very, in some way, unsophisticated, but I will try to show that it has some interest to try to describe how this very simple phenomenon might lead to some structure. So the philosophy is very different from what we had in the previous systems like presented by Julien. We had typically entities that were listening or looking in some way at others. So the influence graph, we could represent it like this. I'm here and I look, if I am a bird, I look at my neighbors, etc. And I have this kind of influence graph. And that creates structures that make it possible for some structures to emerge. And what I will start with an example like that, and to try to show how this can be represented by a discrete Laplacian. Actually, the term Laplacian will play a very important role in my talk. And it is actually, we saw already in these lectures a lot of Laplacian. Most of them were coming from Brownian motion, say, from Fokker-Planck expressions of stochastic phenomenon. The Laplacian I'm going to talk about are in some way very different. They have nothing to do with diffusion processes, but they really encode some structure relation between discrete elements. So here I will show you what I have in mind when I'm talking about discrete Laplacian. And also another keyword that will play an important role in my talk is gradient flow, and we will show that in this, even if it's imperfect gradient flow in this situation. This is something I'm going to focus on. For each system, I will consider to show, does it have a gradient flow structure? And we actually saw in the previous lecture this minus the V, so this is the gradient flow part, even if it was perturbed by some noise. Okay, the systems I would like to show are in some to some extent poorer. Actually, I will concentrate on a bunch of people like you, and actually the influence graph will be much simpler. Those are loops, actually, so there is no collective motion, actually, so let's go to bed. But what I would like to show you is that when you can see that this system, they share the same space, okay? And by simply expressing the fact that they shouldn't be at the same time at the same place, there will be some interaction emerging from this constraint. I will try to show you how this very simple phenomenon of congestion might lead to some structure at a larger scale. And we'll see you. So let me also not forget that first, I would like to cite some collaborators. I will present works done a long time ago with Juliette Venel, also Fatima Al-Reda for microscopic models. Also, I will present you in the last lecture macroscopic model based on optimal transportation principle. They have been done by many women actually in this topic, Aude Roudneff-Chupin. Also my colleague Filippo Sant'Ambrogio. And most computation have been performed with Sylvain Faure, and let me add that we propose to add an extra lecture tomorrow afternoon as 4:30, I think. 4:30. That will be here. For those who might be interested in actually running some computation, we developed with Sylvain Faure Python open source library So you can install it, and Sylvain will present you how to use it. And most of the computation I'm going to talk about and present you perhaps tomorrow, I will give you some animation, can be done with this software. So it's called ChromoSim. You might try to install it by Google. You can Google it, like pip install ChromoSim. For those who are on Windows, Sylvain just told me that there might be some things to do beforehand, like to install some kind of C++ library. So if you have questions about that, come and see me during the lunch break, okay? To anticipate, if you are interested. So you're not obliged to come, but for those who like for geeks, basically, they are invited to come tomorrow afternoon. Okay? And I think that's it. So I would like to start with some large introduction to present you some models a bit remote from crowd motions, but first model of this type to see how the discrete Laplacian can be extracted from the model. And then also an opinion, very simple opinion propagation model, where we will have another kind of Laplace, discrete Laplace, and that would make it possible to ask some question which we will see again in crowd motion problems. And also to present you a very simple way to build a Laplacian out of a constraint. That would be actually the core of my talk, that some structure, this Laplace operator, will come from expressing constraint. It can be done in a very classical mechanics situation. And then I will start to present you some classical crowd motion, make some comment on that, and then get to the presentation of the core of my talk, which will be granular like models. Okay, so first let me present you the so-called Kucker-Smale model, which has some similarity. It's the same philosophy than Wicksek model that Julien told us about. It was first presented, I think, in 2005, in a discrete setting. So you have typically birds, you have entities. They move, the position is xi. They move with the velocity vi, so we have dxi over dt equals vi. Oh, sorry, let me start with, dxi over dt. In the continuous setting, but actually it was written in the discrete way. Let me write it in the discrete way first. Vi k plus 1 is simply equals to the sum, in its very simplest expression, vj k divided by the, for j in some neighborhood. So typically what is considered that you have many entities, so you have a radius, and you considered the neighbors that are within the disk with the same radius. Actually, this was a three-dimensional model, so it's a ball. And you considered neighbors in this neighborhood. You normalize by the number of individuals, and that's it. Okay. So you, in some way, it's very easy to see that you can you can subtract. Sorry, vi k equals to 1 over. And let me write it that way, minus the sum of j vi k minus vj k. So it takes the following form. Here you have a discrete time derivative. So it's Lagrangian. It's important. It's a Lagrangian time derivative. What I'm saying that individuals are followed in their path. Okay. So this is actually a total derivative with respect to the individual, if you wish. And here you get something that you really want to call a Laplace. Let me write it in a vector. If I simply write the collection of vi, it takes the form of the discrete version of some ODE, that is dv over dt, equals to something. Actually, since I want to make the comparison with this system and a PDE, the tradition, I never understood it. When you have ODEs, you put what is important in the right-hand side. When you have PDEs, it's in the left-hand side. So if I want to make some comparisons with the PDE, I will put it in the left-hand side, plus LV equals 0, where LV corresponds to this operator. While L is a Laplace operator, So to be, so this really has the structure of a heat equation, some sort of heat equation on the velocity. Or if you wish, you can also make a comparison with Navier-Stokes equation, or it's not exactly Navier-Stokes equation, but here you have something, some kind of Navier-Stokes equation in Lagrangian setting where you consider viscous forces. Well, this is the minus Laplacian u in Navier-Stokes equation. So it takes the form of a heat equation. Why is it more complicated than a standard heat equation? Yeah?
How do you define the neighborhood? And I guess it's Ni. And
yeah.
You fix the distance?
Sorry, of course, yeah.
Of them, yeah.
Yeah, well, typically there are many ways to do that. Here, typically, I consider a disk or a ball with some fixed radius, okay? And I count the people, sorry for the mistake, yeah, it was not clear. And of course, it's more complicated than that because, for two reasons, because the Laplace changes in time, of course, because the individuals, you might consider a situation where you have an infinite radius. In that case, you have everybody, you have a standard Laplace operator, but a priori in this setting, it depends on x, that is the integral of v. So it's a very nonlinear coupling between both, and also, and yes, this depends because of this, and of course the x's are moving during time. So it's not exactly a heat equation, but as far as you consider fixed situation, instantaneous situation, and you see how the velocity evolves, it's some kind of diffusion process, but not in a stochastic way. It simply expresses that the velocity relaxes to the mean velocity on neighbors. What in more realistic model, they actually add coefficients here that we already saw in Julien-Stokes, where something that decreases with the distance between those two put more importance on individuals that are close.
Sorry, can you please comment? Your Laplacian operator is very non-local.
Yeah, but it's a discrete Laplace operator.
So this equation is written for discrete Laplacian. It is a graph Laplacian.
Yeah, it's a graph Laplacian. It's a Laplacian in a graph sense. Yeah, nothing to, well, it's a discrete Laplace. It contains the structure of the graph, which is actually simple here. You can imagine a complete graph, so you have a Laplace on the complete, but really is a discrete Laplace, and like for electric networks, I will come back to that. It is not meant to approximate. I'm not saying that this approximates the continuous Laplacian, okay? But it really has the same structure, and it has the structure of a heat equation.
And K means unit of time?
Excuse me?
What is K?
K, yeah, is the time. It was introduced in that way for various times, say 1 second, 2 seconds, etc. And I just go fast just to interpret that as a time derivation. Okay, so just to say that when you try to model phenomena with some kind of consensus, like some behavior that tends to consensus, you want to do like your neighbors. It's naturally expressed by something that is a discrete Laplacian. Then the second setting is opinion propagation, which is some kind of collective motion, even if there is no motion in the physical space. Propagation. I would like to present you a very simple model, which is something is very pleasant to teach in lectures, like even undergraduate. Actually, part of it can be taught at a very standard level. So you can see that now that you have a graph, say individual, a set of vertices, which I simply enumerate n, and you consider a matrix of influences. So Kij quantifies the influence of j upon I, and we consider that I, the individual I, shares its own attention among some neighbors, not everybody, but that we have Kij over j, where I consider that all the Kj exist, but some of them are 0. So it's simply a sum in j. And they are non-negative coefficients. No, sorry, not 0. That wouldn't be very rich. equals 1. So we have a stochastic matrix. And, okay. And we can also, so we have a graph and we have a structure, a directed graph, the set of edge of which is the support of the matrix, so the set of ij, couple ij, such that kij is positive. And we consider that we have a set of opinions. So U is simply a vector of opinions. I consider that an opinion is a real, or say, for example, a number between 0 and 1 that quantifies the tendency to vote for certain candidates at a binary election. And the simplest system model you can imagine is the following. It was introduced a long time ago, but we'll see it's quite poor. The basic model is a bit poor, but it's an interesting toy problem. So again, k corresponds to time. In that case, that would be more natural to take days, following 1 day, 2 days, etc. And then you consider that at each time, well, your opinion tomorrow is a convex combination of the opinion of the people that influence you the previous day. So it's a sum over k. So I can, of course, it will imply kij. So I take all of them, and I take 0 when there is no influence. I can also underline the fact that I am only interested in people such that A listens to J, and it's uj k. So it can also be written in a matrix way. So you see, for those who are familiar, since I have a stochastic matrix, you know that you have a random walk associated to this matrix. And if you consider the probability distribution of your random particles, it follows an equation which implies the k transpose. So here actually it's the transpose problem, the usual problem in probability. But of course it shares some common behavior, but it's a different problem. Let me straighten that k is far from, in general, is far from being symmetric. For example, the first time I talked about that, I made some verification. For example, it was the Twitter. I think there are followers on Twitter, and we checked that, for example, Trump, before a long time ago, he had like 40 million followers, and he followed like 4 people or something like that. So it's very, very non-symmetric. Even the support of k, the graph itself is very direct, very unsymmetric. What do you want to write here? No. So let me just try to, I like heat equations. Let me try to extract a heat equation from that. I simply subtract again uik, and I get this sum kij, since I have this normalization uik minus ujk. And here it starts to look like a heat equation. And again, if I write that LU I have formally a discrete heat equation du over dt plus LU equals 0. So L is usually called a non-symmetric Laplacian. So you might say that it's not an actual Laplacian, but still it verifies the maximum principle. So it has some features of the Laplace. So it's in some way you have the right to call it a Laplace operator. In this form also it's interesting to develop. There are many. The model is very poor, as you imagine. It's not very realistic, but it's still interesting. It can be generalized. For example, an interesting way consists, like it was the case for Kirkus model, to replace this linear model by some kind of non-linearity. It does not make sense to put it here, but here you can see that has some kind of human Ohm's law or Poiseuille's law. This tells you that you have some kind of flux of opinion that depends on the difference between opinion. The problem is that this is not symmetric. It's not like in electricity. It's not symmetric. You might have some opinion flux in some direction, and you do not have the reverse opinion flux. So it's non-conservative, but it verifies the maximum principle. And if I want to change to have a richer model, the first situation here I have opinion differences. The basic model is with a linear, the de Groot model with a linear, but you could also imagine to make some more realistic assumption. I saw that there is a poster on opinion propagation. It's a stochastic model, but it's actually the same philosophy. You may, for example, consider that when someone has an opinion that is too remote from yours, you do not listen to them. And so you can cut it. That's what's usually done in practice. You just cut it here. So that's the first possibility. I don't like it too much because it means you see right before stopping to listening, you still listen a lot. So it's very obviously very unstable and a bit unrealistic. You might even consider it a more reasonable thing that you stop listening to people, and possibly when you really discuss with people that are too far away from you in terms of opinion, you do not listen to them. So those kind of models make it possible to recover polarization in opinion. And you might even consider, let me use the last color, but of course you enter a world of pain if you consider that you might have anti-propagation. What I mean is that when someone is not at all fully disagree with you, then you are rejected by it. So it's very difficult because you get some kind of reverse backward T equation, but without any regularizing terms. So of course you may expect something like this, but it's very difficult to study, and it's not clear how realistic this is.
So, but the fact that K is non-negative, is it compatible with the fact that you...
The first model, the linear model K, is positive, is non-negative, so that means that actually you are always tending individually to consensus. You try to get closer to people, and that's also in a more thermodynamical way. It's the maximum principle. But when you put a nonlinearity, you can put ugly things in the nonlinearity. You still keep positive, but actually it's as if the coefficient were negative when you are in this zone. So you have anti-diffusion. So of course you have very unstable, possibly unstable thing. Okay. So you have this kind of heat equation, and this is some kind of crowd motion, even if it's not about motion, it's about opinion. And in this situation, it's quite interesting to wonder whether there is a gradient flow structure. Oh, I didn't say in this, but obviously this has a gradient flow structure, at least instantaneously. This is the gradient of some functional of the velocity that is simply some kind of viscous dissipation functional, the sum of ui minus uj. Like in the Stokes situation, fluid situation, you have the term, the Laplace can be interpreted as coming from the gradient of some diffusion term. So this gives you some kind of dissipation principle. So it's not exactly a gradient flow because the function depends on the time, depends on the position, but it's instantaneous, or at least for a short time, a gradient flow. It's a succession of gradient flows with functionals that changes with time. But still it has these features, and actually if the radius is infinite, you consider all people, then you have a real gradient flow structure in your problem. Okay, the question, we might wonder whether if we consider continuous evolution problem minus, so the matrix I had was, let me forget about nonlinear problems. I come back to linear problems. It's I minus k minus I minus k. So it's a linear evolution problem, not very complicated a priori. Does it have a gradient flow structure? So can it be written like that? The question is not very interesting because the answer is simply that yes, it does has a gradient flow structure if and only if this matrix, that was I was calling L, which is equivalent to K because the difference is proportional to identity, or K is symmetric. So it's not very rich, and there is a little probability if I made an inquiry by trying to build the influence matrix of this room, for example. So I know Laure, I put 0.6 to Laure, and I don't know 0.3 to François Petrelis. And you can imagine this matrix. You will have a stochastic matrix. Does it have any chance to be symmetric? The answer is no. You can see it has obviously a zero measure, so it does not make sense in terms of modeling. More interesting question is the following, which is a very general question that you might ask when you have a problem. I think I realized quite recently that there is a lot of investigation when you have a problem. Does it have a gradient flow structure? But the good question is there a metric for which it has a gradient flow structure? So it's a wider question for which it has a gradient flow structure. And actually the question is simple. If I am in a finite dimensional Euclidean space, so the problem is that my problem star has a gradient flow structure for some metric. If and only if, so a metric is simply a symmetric positive definite matrix. There exists symmetric positive matrix, and when you have such a matrix, it's quite obvious, you probably know the formula. When you have a functional and you take the derivation with respect, the gradient with respect to the metric associated to m, you get m minus 1, the gradient of psi, with respect to the standard, the initial metric. So the answer is simply that mk is symmetric. This is not so easy to check, actually. If you have a matrix, it's a stochastic matrix, but it does not have. Does there exist SPD matrix that this one is symmetric? It's not an easy problem, actually. I don't know any software that commonly does that. So it's not so easy to check. But what is important is that this might have some interest because this is in some way generic. What I'm saying is that if you consider a stochastic matrix and you wonder whether it is symmetric, even if you have some of them that are symmetric, this is you do not have, it has empty interior. It has zero capacity. It's a very small set. So it does not make sense in practice. I might say that in reality, no matrix is both stochastic and symmetric. But here is different. If you consider a diagonalizable matrix with real eigenvalues, if you perturb it, then you keep this property. Yeah, well, I have to say it can be shown, it's an undergraduate exercise, that this is equivalent to the fact that K, sorry, I forgot that, is diagonalizable with real eigenvalues. And this is stable. This has non-zero interior, so it really makes sense in terms of modeling. And let me finish with this model, which I find interesting, and I might come back to this situation by just saying that there is a special case where M, the metric, is diagonal. So M is equal to, so you can see that there are masses associated to people, and actually we call that, this was done, sorry, I forgot to cite it. I did that, it was for another summer school actually, with Hugo Lavenant, but it was more interesting that we saw it. If you consider a diagonal, so this MI can be interpreted as masses, but also we call it charismatic networks because they can be interpreted as charisms. Let me show you why. This means first that MIKIJ equals to MJKJI. So this simply expresses that this. And this, for those who are familiar with Markov chain, this means that the associated Markov chain is reversible. And in that case, if you write that Cij, you end up with a problem that really has physical structures. What is interesting here, when I have really non-symmetric situation, it violates the principle of law of action and reaction, and so it's really something that reflects the human behavior or the social feature of the model you are considering, because you have non-symmetric, and that's typical of social interaction, that they are non-symmetric, whereas in physics you have this in it's very common in most properties in physics that you have this principle of action-reaction. But,
sorry, Bertrand.
yeah.
So the mass is sort of an inertia and opinion, so how, you know, I'm going to keep my opinion for a while, but it's also how often I change neighbors.
Oh no, there is no change of neighbors. First, there's the connection is the same, or you can even take a complete networks, but with various Kij. And here the Kij, that's a good point. You have very interesting model, and I think very difficult to study. I tried, I didn't succeed yet. When you want to have the Kij evolve in time. So you change, which is very realistic. For example, if someone has an opinion that is very far away from yours, you just reduce the corresponding Kij. So it's very couple problem. It's complicated to see, and what you can observe numerically, that you end up with a polarization. You have groups of people that think exactly the same, but they have different opinions. But it's difficult to prove. But your question was, yeah, this is some kind, it can be seen as some kind of inertia. Let me just write the equation. It takes this form, equals minus sum of Cij. So Cij now is symmetric. It quantifies the bound between two people, but which is like some kind of friendship intensity, but in a symmetric way. But the relation is still non-symmetric because of the mass. You can be someone with a lot of charisma. You are close to some other that looks at you like a god. So you will not listen to him, almost not, always a little, but almost not. But he will be influenced by you, and that's what is here. Uj. Okay, and this model, it can be seen. This is a real heat equation, meaning that if you have, like what in undergraduate, when you consider thermodynamical systems. Each compartment has a uniform temperature, and the temperature exchanges. So the exchange coefficients are theCij's, so they are typically correspond to a symmetric situation. And the Mi are the thermic capacities. So this is not a mass. And of course, you get conservation. You have some kind of first principle of thermodynamics. You can check very easily that the total heat, that is the field of temperature, which is an intensive quantity integrated against the natural measure of the system, that is the measure of mass or of charisms, of heat capacities. This gives you the total heat energy that does not vary. And this can be shown. So you recover in this situation a standard physics, all the. And actually, it's closer to the models we are going to consider in a few boards. Okay. Let me just, to finish with this. This is quite unrelated to the topics I would like to address. Just as a question, a question we try to address, and we have some partial answers. But I think the question is nice if you want to model things. Imagine that an opinion is no longer a single number, but is a number together with some sort of self-confidence, well, a quantification of your self-confidence. You might think 0.5 and be very convinced of your 0.5, or not so sure. So in that case, you want to consider that an opinion is a number and a standard deviation. So let's consider if you still have 1D opinion. So you have U and sigma. So you present an opinion by this couple, and you want to build a model that models the evolution of both the temperature, the opinion and the standard deviation. And the question, this is a modeling. This is not an easy question. Imagine you have no personality. You discuss with someone that thinks you want with strength or with standard deviation sigma 1. And you discuss 1 hour later with another one, you two, say a Zemmour guy or and the Mélenchon guy, well, too. But you have no personality. You just listen to people, and one of them, for example, is very convinced, and so sigma 1 is small, and the other one is not very convinced. Sigma 2 is small. If you want to write another the same model, you want to interpolate. Even in this simple situation, you have 1 and 2, and you look at this one, you look at these two, and you would like to get the interpolation between those two opinions, which I could write. It's bizarre, but sigma, if I think it's okay. So that would be the interpolation. You can convince yourself that if you just perform the linear interpolation between the opinions and this really does not make sense in terms of realism. So that's just a question. If you want to, we have some partial answer to that. You can come. Well, I can come back to that if you are interested in it. There is a funny way to interpret that, to respect the fact that the opinion. What is important is that this interpolation is not supposed to respect the maximum principle, because if you are two people, one that thinks 0, for example, 1, and you have the interpolation, okay? There is a way, I will come back to optimal transportation, that would be an idea to interpolate, that would give you, if you discuss with the Zemmour guy and very convinced, and then a fanatic Mélenchon guy, then you end up by thinking that, okay, the answer, I am sure that I am a Macronist. You see what I mean? I don't know if you find that realistic, but I do not. So that would give that. Optimal transportation would give you that. So what you expect is that you really, if you have no personality, you won't be sure, and you want some kind of opinion that makes both opinion possible. So you would like to expect some kind of thing like that with a large standard deviation, which obviously violates the maximum principle as far as standard deviation is concerned. See what I mean? So if you want to think about that, you want to find a way to interpolate between things, but this is clearly not linear interpolation on that.
Sorry, is this the Wasserstein-Barry center?
Excuse me?
Is this the Wasserstein-Barry center?
This is the Wasserstein-Barry center. Yeah, which is not actually good. I love optimal transportation, but this is really a situation where it does not give a satisfying answer, clearly. And that would be, there have been some variations of the Wasserstein-Barry center that might go in the right direction, but the idea actually we had is different. Okay, so the last example I wanted to show, it's very standard and like undergraduate, like physics, but it's something that contains the techniques I will use to build, to extract the Laplacian from the granular models I would like to show you later. Wow, it's far away. So the situation, my third situation, is that I have a networks of, you can imagine if you like fluids, for example, that might be the lung, you can consider that a set of interconnected pipes. So you have a graph, they are not necessarily straight. And so you have vertices. And you consider, I don't prefer a fluid of electricity. It's exactly the same you can consider the dissipate. Let me consider the notation are closer to the fluid setting. So I consider that Uij is the flux of fluid going through the Ij pipe. Considering I have some connection, the V is a set of edges. So the network is undirected, but you have some fluxes which are Uji is minus Uij, like in electric network or fluid network. Is a flux, and yet you consider the dissipated energy. That is Rij, Uij. So this is Joule's law. Remember that in the notation is more like in fluid, where U sounds like a velocity. But if we were in electricity, I will call that I, capital I, and this is Joule's law simply. But we have the same with fluid. When you breathe, you dissipate energy according to this, and I will add a half because I will take the derivation. So up to a constant, this is the dissipated energy. And then I would like to consider the very simple problem, which is close to what we will meet after. So that might sound bizarre. It's quite remote from crowd motion, but it's actually close. The problem I would like to consider is that I have prescribed fluxes, meaning that for all vertices, the sum over neighbors of Uji equals to 0 or some prescribed flux, meaning that I have a network and I have the Kirchhoff law at some nodes, so there is no leak here, but there might be some exchange of fluid with the external. So I have this conservation. Of course, obviously, it can only exist if the sum of the BI's are the same, but this is implicit. For the lung, for example, that would be here the trachea. You have some exchange with the exterior, and at the end, you have exchange with the alveoli. And here, you do not have, you have BI equals to 0. Okay, and the problem, a very standard problem, consists in minimizing the dissipated power. So it's something actually, it's a shame. It's very simple. I realized it only a few years ago that actually Poiseuille's law or Ohm's law can be recovered quite in an abstract way. You know that they are phenomenological laws. They can measure electric potential, you can measure pressure, and I guess the way they were established was phenomenological, but they can be in some way considered as the consequence of some kind of abstract minimization principle. That's what I'm going to do. You minimize this on the condition that BU equals B. So B is a matrix that expresses all those lines. A row of B corresponds to this, is associated to a node at which I have some conservation properties. Okay? And now, so I would like to spend a few minutes to make very elementary calculus of variation, probably very easy for some of you, but some of you might have escaped to that. So I would like to show you something very simple that will play an important role. So I have to minimize some functional where U is in Rn, and under some constraint I want to minimize psi under the constraint that it belongs to K, where K can be written as U0. That is any solution of that. There is a U0. You can show that if B has 0 sum, then there exists at least a solution to this equation. So you take any of it, and what is important is it has to give the same values with the kernel of B. Okay, so you want to minimize the smooth functional over. So the functional is strictly convex, it's coercive, it goes to infinity when the norm, it could be taken as a Euclidean norm. So it has a minimizer. It obviously has a minimizer, a unique minimizer. And I can write it U. And you can characterize it by simply saying that psi of U plus, I want to write the fact that U minimizes this. For this, I can add any vectors such that this is in K. And since K is an affine space, here it's enough, it's exactly equivalent to add something that is in the underlying vector space. Okay? So here I can add any element of the kernel of B. So I'm going to write plus TH for all H in the kernel of B and T in R. And here you make a first order expansion okay, and you consider that. So you have a first order expression in T. So you fix H now in kernel of B. And for any T can take positive or negative value. You have that it has to keep a constant sign. So if this is non-zero, that cannot happen. So necessarily this is 0. So the gradient of psi at u dot h is 0. It means that that the gradient of psi at u is in the orthogonal. So h was describing all the kernel of B, and the gradient is orthogonal to any of such vectors. So it's in the kernel of B orthogonal. And you might remember from I don't know if you used it, the first time I used it was for this, something you learn in undergraduate classes, that this is the image of B transpose, which I'm going to write B star, the adjoint of B, because it makes sense in an infinite dimensional networks. So it means that there exists some lambda which belongs to the image of B, such that the gradient of psi of u is equal to minus b lambda. So usually we write it like that, equals 0, and you have also bu less than b. Equal. I will later on that will be equals to bu0. And it takes a saddle point form. So this is b star. So it has a very common form. You know, I'm sure you know a lot of equations that have this form. This is the basic for obtaining a lot of equations. For example, in fluid mechanics, Stokes equation, where here you have the dissipation. When you take the gradient, you will have the Laplace. And here you will have the divergence, or minus the divergence, the adjoint of which is the gradient. So that's the trick that makes the pressure exist in fluid mechanics without even trying to measure it. Here it's the same. It will, let me write it P instead of lambda, because actually it will be interpreted as a pressure. So the pressure appears as a mathematical auxiliary that does not make sense physically, but we'll see that it really has a meaning. So this is very general. Let me just, because we will come back to that at some point for macroscopic model, we will be in the very same situation in the infinite dimensional setting. So I don't know, here I was in the finite dimensional setting, so B is a matrix. Does it work in the infinite dimensional setting? Actually, it's not so difficult to generalize it in the way that you just consider that B is no longer a matrix, but an operator from an infinite dimensional space to an infinite dimensional space. This is fully, I did not use any compactness theorem or anything. This works in infinite dimensional, that's why it works in fluid mechanics. The only, there is yet a problem. Do you see where is the problem for an infinite dimensional setting?
Or something in this.
Here?
Yes.
Yeah, this is not true, but this is almost true. Actually, what is true in infinite dimensional setting? This is a vector space, so it's, of course, it's closed in a finite dimensional setting. In an infinite dimensional setting, it's not necessarily closed, but it works fine if you add the closure. So this is true, but of course, this is not true. What is called the Lagrange multiplier does not exist if the image of B star is not closed, which happens. It's not bizarre. You do not need the axiom of choice to build a counterexample. It really exists in real life situation, if I may say. And but if you show that the image of B star is closed, then you have the same possibility to build like a pressure in most fluid mechanics model. Yeah.
B is a complex operator. Why is there a B star?
No. Sorry, it's not complex, it's adjoint. What I mean is that in finite dimensional setting, nothing is complex. I only have real space. But if I have B, that is the V and lambda, which are Hilbert spaces, real Hilbert spaces, simply you will say like BV Q, if I identify spaces with a dual space, so I have a real dot product, is equal to B star Q dot V. Okay? It's the adjoint. It's no mystery and nothing complex. So But okay. And we'll come back to that. We'll need such property. And this actually plays an important role, and the difficulty of what we are going to do afterwards is that when the equality constraint, this one, is replaced by inequality constraint, this does no longer work, so you have to develop more sophisticated strategies, but it really has the same structures, as we'll see. Let me check. I started at, just to have a 45 minutes ago or something. It was, oh no, it was 11. I have 40 minutes? Okay. Okay, yeah. Okay, let me finish this example to get, what I'm going to do is to recover Ohm's law or Poiseuille's law by purely mathematically, if you wish. The pressure is nothing that exists. It simply stems from this approach as a Lagrange multiplier, but you see here, P does not is not at all related to my physical problem at first. But we'll see that it has a meaning, but you can see that a posteriori. I can write it here. So what does it mean in our context? So psi is a very simple functional, is the dissipated energy. So the gradient of that, meaning I have degrees of freedom that are the uij's. When you take the derivative with respect to one of them, they separate. It's simply a sum. You get uij itself multiplied by arj. So that will be simple. Just let me see. Let me try to represent what is B. So B, each row of B expresses a constraint at some point, and the variables it acts on are the fluxes. So a column of B corresponds to uij, and uij will excite two nodes. You know, uij corresponds to an edge. It has two ends. It has ends I and j. And when you consider this, where did I put it? Here. When you have, here you have uji, so it excites, meaning that actually it's reverse. It will excite I with a -1. When you derive, since it's linear, you have 1 or -1. And you can check that here you have -1 and 1. So the matrix B contains only 1 and -1s. 1 per each column and 1 -1 per each column. And when you take B transpose, what you end up with is so I told you that when you take the derivative of this with respect to uij, you get rij uij, and then you check, then this B star P will simply give you minus pi, because here you have a column B star, you will have a row with this -1, 1 at I and at j, so you have this pj equals 0. Okay, and this is Ohm's law, which I guess you learned it as a phenomenological law, but it can be, it is the same in fluid mechanics. You have two ways to build pressure as a physical, as something you can measure, you can explain, like in Feynman books, like with the shock of molecule. But for incompressible fluid, you can see that as something that is purely mathematic. And here I have Ohm's law or Poiseuille's law coming from mathematical arguments. And that gives you, is something that we will use also in the crowd motion model with unilateral constraints. Okay, so let me start by talking about the topic which I'm supposed to present you, which is crowd motion, but you will I hope you will understand why I presented all those various models. Crowd models. I will start with classical ones, and historically it's not such a old topic. Actually, it started in the 90s, mostly, at least for microscopic models, by the so-called social force model. By Dirk Helbing and his team. And there is a paper in Nature, I think, in 1995. I have a list of papers which I wrote myself with collaborators and other. I might share it with. Perhaps I will give it to you. This is actually based on very simple principle. Is that you have been doing particles for centuries. You want to model people, so you say, why wouldn't I consider people like particles? So people are particles with a mass, which is an actual physical mass. It's not an abstract mass, and the velocity. So you have a Newton law that you write for people, with some sort of term which encodes the tendency to go somewhere. So this will be an assumption that we'll have in most situations. You have a desired velocity. Let me write it like that. UI, this is where you put possibly psychological modeling. This is UI is the velocity that the individual I would like to have if they were alone. Okay, so it corresponds to the goal, for example. So of course it might depend on their own position, but also on the position on others. There is always an ambiguity in which we are going to put some interaction terms in the equation, but you can also put more sophisticated interaction here by considering strategies, etc. So let me say that Q, what is used, Q minus I, is simply the Qj for j different from I. And then you have a relaxation term with a minus, I can write it like that to have a characteristic time. So it can be seen as it's a bit as if the particles were glued in a fluid that goes at a viscous fluid that goes at the velocity that corresponds to, for example, the escape velocity that you want to escape, that you take the shortest path to the exit. And there is a frictional term of the Faxens type, for those who know, this is the interaction between a small particle and a viscous fluid, which is linear. So it tends to relax the actual velocity toward the desired velocity, okay? And plus some interaction term. I will not go too much into detail because it's not the core on my class. But for example, if you come tomorrow with Sylvain to Sylvain's lecture, we have in this Chromosym software, we have this model that is implemented. So Fji, this is the action of j, individual j over I. So typically Fji would be minus the gradient of some functional. Here we cover this gradient flow type phenomenon that, say, depends on the distance. I will write Qi, the distances, like in granular materials. Qi minus Qj, where phi is a potential interaction potential between two particles that encodes are they willing to be together or not. So typically what is encoded in this is some tendency to not to be too close to people you do not know too much, which is we are not too familiar with someone. So it is something that has been studied. It's very interesting literature about that. There is in particular a book by Edward T. Hall in the 60s, I think, the hidden dimension. It's more literature than science or social. Well, American sociology, hidden dimension, the hidden dimension. who made some inquiries. Do people, depending on their nationality, their culture, etc., at which distance do they tend to be with respect to neighbors? And it can be shown that for European, for Americans, it can be different, but typically you have this tendency, and you can put a repulsive potential. If this is 2 times the radius, if you assimilate people with disks, 2 times the radius, so that would correspond to contact, and that would be what is called the proxemic, the extra distance that you want to add between people. And whenever this distance, the actual distance gets below this value, then you have some repulsion potential, which might look like that. You might also imagine that you have some attraction to it. It looks a bit like flocking models like Vixek, etc., but there is no velocity here, so it's only on the position. So you might imagine some terms that you are influenced not only by others' position, but by their velocities. But in basic model, they mainly use forces which only depends on position and not velocities. And you might imagine that people want to be together, so you might imagine some attractive potential for, I don't know. You can put all the physics you want or the sociology you want in this term. You can also, there have been many extensions. Actually, it's a bit, I think it's a bit bizarre because it's in modeling, something does not seem very logical. For example, pedestrian modeling can be considered as quite close to car traffic modeling. And then if you ask the question, is it natural to take into account inertia in such models? The answer that pops in my mind is that when you have a car, you cannot stop abruptly, so really you have to take into account inertia. For pedestrian, if I decide to walk, I immediately start to walk. I'm not yet at least so inertial that it takes me a few seconds to walk. So and there is, when you have a collision, it's clearly a non-elastic collision. There is no inertia, but in the reality, in the modeling world, the model that has a great success, and in all industrial software, that is the model that is used, is inertial. And for cars, mostly the models which are the most commonly used, like LWR model or follow the leader model, they are first order. So this is really the contrary. And I cannot explain that. But it's just, I think I might say, well, I am film, so perhaps I shouldn't talk too much. But I think that it makes the possibility to tell a story about that, because it was called social force model. So you have an analogy with particles, but in some way, I think it's not so useful. And actually, even in commercial software that are sold right now, since it's inertial, for example, those forces, you have those bizarre things. For example, when you have a line and someone comes here, it might start to oscillate with respect, which is natural because you have some kind of Hamiltonian structure here. You have energy conservation, like spring mass system. So it oscillates, it makes bizarre things. Whereas it's very easy to write over damped, but up to my knowledge, it's not almost never used, this model, whereas it seems more reasonable. Over damped social force model. That would be simply UI. You directly give UI as the desired velocity, plus basically you formally obtain it by having mi, or there is various way. For example, by having tau go to 0, and you suppose that the interaction force follow this tendency. So tau goes to 0, and you will drop the inertial type. So we identify U to UI up to some correction. So those are no longer forces, but velocity correction, and it takes the form, but it really has the same spirit. The sum of AJI and the FJI, they come from force, but they are more velocity corrections. Anyway, this in some ways does not make sense from a physical standpoint, because of course when I try to avoid someone, the guy does not exert a force on me. This is me that decide to do this. From an energy standpoint, everything comes from the individuals and not from others. So in a way, it's bizarre. This term also is not very pleasant, because from an energy standpoint, if you want to get an energy balance, you multiply by ui. So here you get the derivative of the kinetic velocity. Here you get the variation of the potential energy. That makes sense. Without this term, you have conservation of energy. But here you get something that is u minus ui dot ui. You don't control the sign of that. You might be, if you are accelerating, you need to put energy in your system, but if you are decelerating, you lose energy. You do not need, you get some energy if you, in some way. Okay. So this is for, we'll come back to that when I present some animations. I would like to present to you a model which is the closest to statistical physics, since I see that, I know that this is a conference statistical physics, and I'm afraid that what I'm talking about is a bit far away. But there is a model that is really in the spirit of like Ising model. And I'm not a specialist on that, but I would like to present it. It's actually quite interesting to, it can be used to model quite interesting phenomena. It's called cellular automata. It's also included in the chromosome package we will present to you tomorrow. So here you have a grid like Z2. Of course, in the bounded space, you have a, you model evacuation of a room, and you have a door that is say 3. Typically is 0.4 meter, the cell, because the idea is that you can have 1 or 0 person in each cell. This is a strict rule that you have. It cannot be occupied by more than 1. And you have those particles move according to some rules, stochastic rules. Basically, when you have a particle here at some point, it has some neighbors. It might have some neighbors, say 2 here. And there are different ways you can take the von Neumann neighborhood, but let's say usually it's what it's done actually, north, east, south, west. So you have 4 possibilities, but when you have already someone, you cannot go there, even if the guy is going to leave at the next step, but you do not know it yet. So you have 3 possibilities. So here you have on a cell C, and on a cell C prime, you have a weight that depends on C and then C prime. But the idea is that you have some goal, that is, for example, some point corresponding to the exit. You have the distance to this point. So when I write C prime, I identify it to the center of the cell, and this is a point x0. So the weight is, for example, E minus some coefficient times the distance of, let me say, xc prime. Xc prime is the center of the cell, minus x0, x, or let me write f, exit, is the common goal of people. They want to be there. So this is, when you are closer to the exit, this is larger, okay? So you have some weight, and then you normalize them, PC prime equals to, you normalize to have a probability distribution, the sum of the weights, divided here by 3, for example. Yeah, and if you have zero possibility, you just don't do anything. Okay, so you have probabilities, and then there are many ways to do that. I stick to the one I prefer. You can do things in parallel. So you have all the people, and then you make a first step according for each people according to those transition probabilities. So you have a new configuration that might violate the the occupancy constraint. You might have two people in the same cell. In that case, you handle the conflict. You see there is a conflict. You say, for example, you take one of them randomly. Perhaps you take the less motivated. There are various ways to do that. And the one that you picked comes back home at the place. Okay? So in that case, you get, it goes, and I will show you some example. What is interesting is that there is a way to handle conflicts, and it's the first time I'm talking about something that I'm going to talk about later. That is an interesting effect. That is in some way the goal in crowd motion modeling is to be able to recover and understand this effect. It's called, the first one is the capacity drop. And the most interesting is the faster is slower effect. The capacity drop is simply that is not by pompiers, by people, specialists in emergency situation. When you have many people that want to exit out of a room in a panic situation, it's not very efficient. The more people you have, the less fast it goes. Okay, so you have the capacity of the door is typically the number of persons per second that can go through it. When you have many people, you have this capacity that drops possibly down to 0, as we will see. If you have a clog, you have really a jam that stops everything. And this is in some way connected, faster is slower effect, meaning that at least in some situation, when people are more aggressive or they want to go faster, it actually goes slower. So it's counterintuitive effect that you can try to make I don't know if you have ideas in mind. It's an interesting question in modeling that you might ask yourself, how many systems do I know that behave that way? Meaning that you have some kind of physical system that is forced, and when you force it, you get some output, okay? And if you have no force, you have no output, okay? But you have, for some system, if the input is too large, then the output starts to decrease. You have a counterproductive effect. And it's interesting, I found a few models like that. It's not so easy to build, but you can build experiment which corresponds to that. Here it's typical this effect, and it's not so easy to reproduce. How can you reproduce with that? What people do, and I think the idea is nice. Basically, let me at least cite somewhat my German colleague Chad Schneider and collaborators. It's to introduce some sort of friction for conflicts. The idea is that, for example, you had two people here. This was empty, and they both are in the same. Perhaps let me make another example. Perhaps they were initially here and here, and both go in the same. Okay, and the idea is to say, as I said, to handle the conflict, they considered that you just sent one of the guy home. And that's it. But you can also consider, which makes sense in some way in modeling standpoint, you have some friction coefficient, mu 0, which is between 0 and 1, which is the probability that in case of a conflict, nobody wins. Okay? And people, they prevent each other from going forward. And nobody wins, everybody goes home. And its mu is large, meaning that if people are more aggressive, they want to go, there will be more conflict, and conflicts are bad, so people go back home. And it typically considers, if you have taken the Parisian metro or RER, when you have these concentrating fluxes, meaning that it's better to be polite in some way. If you really struggle, you might lose some time, or you see by having this jam situation where people do not want to let others go. And this is what is expressed, and it can be recovered. It does not reproduce exactly what happens in practice, but it's a nice way to do that if you have some friction here, mu is not 0, then if you increase the tendency of people to go forward, then you will have more conflict, and conflicts are bad, and it will be negative on the overall flux. So it's a way to reproduce this phenomenon. Yeah?
So
in this model you can increase the tendency of all people involved to move, right?
Yeah.
Because if you were from an individual standpoint, then maybe being more willing to go decreases the overall current, but makes the single individual get out faster.
I'm not sure what I think. What did you say just before the end? Is what did you have in mind? Like an individual?
Like if it was an individual based model, then maybe the will of a single individual to go fast decreases the overall current, but makes itself.
Yeah, there are many actually complicated questions. I don't know if you're meaning, because what can be done is that you can have a behavior individual that depends on what they see around. Basically, this is not the case. This is a blind model like most model I would like to will present. Particles are blind, they just go and then they see what happens when there is conflict. They are just passive on this. But you might consider that what we try to do sometime, try to record the fact that it's good to be polite. For example, if you are you accept, if you are in a situation where you guess that some people are going to take the case, you do not struggle for it. So you can include that. And but your question was perhaps, is it really worthwhile? There is another related question that might be closer to the one you had in mind, is that you can show that globally it goes slower when you have conflicts, but it doesn't mean it does not give you answer. If I am me, do I have to be aggressive? May I win by being aggressive? And that might happen sometimes, that yes, you have interest, even if it's bad for the whole community, then it would be interesting to be unpolite. But here basically unpolite people pay for that. It's quite a moral, it's auto-regulatory in some way, because you do not really have interest. Everybody loses, but you included in most models. Well, the best way is if you are very unpolite, but all the rest is very polite, you are the king. Yeah, that's for sure. But at least as soon as you have a few unpolite, they really struggle. I can show you some pictures about that, perhaps tomorrow, animation. So just like 15 minutes. Oh, okay. So perhaps I.
Sorry, could you answer a question on this? Sure. Just think on the metro that two people, if they want to go to the same place, sometimes they agree to slip past each other and replace. Like I'll just go to the side.
Yeah, here there is no negotiation, but we could imagine I'm not sure that it would be this is very rigid in terms of directions, and so perhaps it's not the right framework to do what you have in mind. But in some other models, that's something well, I'm not going to talk about game theory, but really we have started to talk about that. The real crowd motion could include some ingredients of game theory, and actually the lecture by Cécile, I don't know if she left. Oh yes, we'll talk about that. If it's really important to anticipate what other people are going to do, and that's what here it might make sense. What we have done for the time being, because game theory is very complicated, and you have some Nash equilibrium that possibilities, but you don't want to pick at least. But she will present something based on mean field games, for which there are quite interesting results. But what can I say? What we did, for example, what we started to do, but it's very difficult to formalize, is that, but it corresponds to when you are Châtelet, for example, it's the large area station, and when you have people going, when you want to cut a line that exists and people don't look at you, you actually perform some kind of shortest path algorithm, aconal equation, but in a moving environment. We did that possible. So you are in the space-time, and people that move are like cylinders here, and you have to find a way. You have a constraint on the vertical velocity, the horizontal velocity, which corresponds to the actual velocity, because the vertical variable is the time variable, and you want to do that. So if you consider that you extrapolate what people are going to do, what you do actually is to try to find an optimal strategy assuming that people are going to do. The problem is that if everybody does that, you of course you change your own strategy. So here you have fully something that is quite completely reflexive, nonlinear, and game theoretical, complicated. Okay, perhaps before I get to the rest, I had the game in mind. I think it's quite, since we are talking about game, it's not very serious, but I would like to perhaps not to play in practice. To play it really, I should have like 10,000 euros and say I will give it to the winner. So let me imagine that's the case, and but keep in mind that it's not. I should have taken something to symbolize that, but I really have nothing. The idea would be, and we can play it if you wish. If you can send me an email. The rule here you are about 100, and the idea would be everybody chooses a number between say 1 and 50 or 1 and 100. Say you don't say to others, but you send by email to me. You send the number between 1 and 100, and the rule is you get the number. Your score is the number you picked, unless somebody else picked it. Okay, in that case you get 0. Okay, and then everybody has a score, and the one that has the highest score gets 10,000 euros. I don't know if you see, what would you pick as a number? And it's not very interesting. You can play with 2 players. It's quite interesting actually. I did that once, and we even filmed that experiment like 100 times, the same game with the same players. And it's very interesting in the psychological. Yes, you pick a number between 0 and 3, and you have to win. And what happens is that usually after a few times, you have the strongest one of the player takes 3 and the other one takes 2, and okay, it's okay. If the idea is that if you have 3, then you get 3,000. If you have 2, you get 2,000. Then all people are about happy, so they play. And I found the day I made the experiment, they were very aggressive. There was one student, PhD student at École Normale Supérieure, and another was a journalist who was making some reportage, and actually it didn't. They lost everything. It was really a conflict without resolution. So it really say things on people. So I don't know what you can imagine. Perhaps we are not going to practice it, but you can imagine what would you play in this situation between 0 and 100. There are 100 people. I pick one, but if someone else picked it, then I lose everything. And but one shot play. Well, you can come back to me. I would be very interested to see what would you have played if you really had the 10,000 euros in mind. So let me perhaps in the few last minutes, like have 5 or 10 or yeah. I will present you some macroscopic motion, and then I will start tomorrow with the granular models I wanted to present. In the literature, why did I talk about this game? Of course, okay, the guy is getting crazy, he's hungry. No, it's just that we are going to see that what happens when you have people getting out of the room is a bit the same. You have you struggle for the same space. If you know that if you only struggle to the end, you will lose everything because everybody. So it's better to be polite. The problem is that if you don't know if the guy in front is going to be polite, it can be a catastrophe. And the game reflects that. If everybody is modest, it is possible in this game that nobody plays 100. That's why I would be interested in. You see what I mean? You can hit for the stars, but if you are a bit afraid, you might not dare play. That would be a pity. And that happens in crowd motion. If people are too polite, then okay, go ahead. You do not dare advancing. It really you do not have aggressive jumps. You have some kind of jumps also. So the best, I think, is the mixture between both. Macroscopic models. So as I said, the macroscopic models were developed a long time ago for like I don't remember the acronym, LWR model. When you have typically a road, so it's for traffic law, but it can also be one-dimensional pedestrian model. everybody goes in this direction. You have some kind of reference velocity that you would have if everybody, if you were alone, say some real number that is common for everybody, then if it can be changed. And you model the crowd by a density that depends on x and t. And you have a transport equation, so dt rho plus dx v rho. So let me forget about x and t. Everything depends on x and t. So it is just a conservative transport by a velocity v, and v in the basic model is simply a function of rho, v of rho. For example, some reference velocity times 1 minus rho over rho maximum. If you considered 4 cars, for example, this rho max corresponds to the maximal density situation. We have vehicles almost touching. And this is actually a not so easy problem. It's a toy problem. It's well known now. But in finite time, even if everything's very smooth, as you probably know, it may create discontinuities. Okay, so classical solution, as you may, smooth solution do not exist for infinite time. Even for, in this case, for very simple, typically the situation that you can have in mind is this situation. So here you have a jam, and here you have people going fast, and this will create at some point discontinuity. So you cannot use standard tools to handle that. So you need to define weak solution that I guess most of you know that you can define by using regular test function and write that this is verified in a weak way. You multiply by a smooth function, you integrate by part. So you have a form of the equation which is formally equivalent, and that makes sense for non-smooth function. You say that, okay, this is a solution, a weak solution, but then you have too many solutions. You have too laxist, I don't know if your term exists in English, but you are too open-minded. There are too many solutions, so you have to put some extra entropy solution, if you know, but it's not the main topic of my talk. Anyway, it's interesting. It works quite fine. It's a first-order model, again, for traffic flow. That's what I said before, and it's the one that's the most commonly used. And you can have direct extension, and in a bizarre way, it has not been used so far. I couldn't find actually many papers on this kind of 2D. What would be a 2D version? There are actually more complicated model than that, but this model, I couldn't find it. In 2D, so you can, for example, consider that u of x is a desired velocity field. For example, if you want to evacuate a building, is the velocity you would have to have if you were alone, say at constant velocity, you follow the shortest path to the exit. So here, if you have no obstacle, you just have straight lines, but it could be more complicated if I'm here, go around the table. So it's the geodesic distance that you want to go in the steepest direction of. So this is given, and you can imagine, the simplest model you can imagine is dt rho plus the divergence of a priori that would be u rho if everything was fine, but when you are congested, when there is congestion, you cannot go so far, so you say that the velocity is slower when there is congestion, so it amounts to multiply, for example, by 1 minus rho, and u depends on x. So it's not so easy because you go out, of course it contains this problem, it's strictly more general, so it's you can have some discontinuities that will happen, so you have to define weak solution and possibly to get uniqueness entropy solution. But so you have all these difficulties, and also the problem is that the theory that has been developed for this kind of equation usually is based on the assumptions that nothing depends on the space. You have no explicit dependence on the space. It has been widely developed to model fluid flows, gas flows, for example, like Euler compressible flows. And in that case, you consider that everything, the physics is the same at every point. You have gas in an empty space, if you wish. But in fluid, in the crowd context, it's natural. Of course, it depends on the geometry. Yeah, sorry.
For
Is usually coarse-grained from a microscopic model?
Excuse me?
Are these usually coarse-grained from a microscopic model? Because I would, in theory, you would have gradient terms that would stabilize interfaces if it was coarse-grained.
Okay, you mean are they obtained rigorously from a microscopic model? Yeah, actually that's an issue that I will address later. It depends on the way the problem. We'll see. I would say no. At least for the models I would like to consider. One of my main message during the 2 next lectures is that the microscopic models and the macroscopic are very, very different, and the one is not concerned. What will happen, this is very typical of crowd motion, so it's not so directly related to fluid mechanics, for example, is a problem of scale, of space scale. The big problem in crowd motion, what is important if we want to evacuate this room, is to go through this door. And the problem is that this door is just 3 times wide. Basically, you are interested in making fluid mechanics like Navier-Stokes or Stokes. You have fluid going through very tiny holes that are about the time of the particles you consider. So, of course, the continuous model does not make sense, and everything is granular. So, I would say yes, if you are in an open space, these particles, and that's why it's very different, I think, to talk about crowd motion or cell motion. When you have cells, you do not force them to go through tiny doors that are 2 times their size. Usually, well, we did actually with some colleagues in Grenoble, but it was for an experiment. I will show you that today or on Friday. But usually, you consider large motion, and in that case, usually you have at least formally, you can get from the microscopic situation to the macroscopic situation. The problem, again, on crowd motion, if what is interesting is what happens close to doors, and the doors have the size of the particle. So it's really microscopic, sorry. So sorry for the bit complicated answer. You can come back if it's not, if I did not answer your question. Okay, so this is an interesting, and as far as I know, there is no paper on that, but there are more complicated papers, but not on that one, which is quite natural, actually. So it's not very sophisticated, because in reality, what might happen if there is I don't know, a jam here, people might go around, which is not contained here. But there is a model that exists, proposed by Hughes. I think there's the seminal paper is in 2005. It's a bit this kind of model, DT rho, but it's much more sophisticated than that one. Gradient phi, gradient phi, and say rho and v of rho. So you have a scalar function that depends on the density that might be typically 1 minus rho over rho max times typical velocity. So this is a transport. So this will give you the speed, and this gives you the direction. So this is the only difference with that, is that you have a direction, and the direction depends on this function phi. I don't know why it's not minus, I forgot. Well, I will see, depending on the way I define it. The solution of a so-called aconal equation. I don't know if you know, it's a bizarre PDE. It's not an evolution equation. You do not have a time derivative. It's an instantaneous equation. And a very, what? I was at it. Okay. Well, one over, but anyway, I will start with that by giving you some example. And this is an interesting model which has drawbacks, but it's an interesting macroscopic model. And then I will start the granular model. And sorry for the delay. Okay, thank you.